So now when you go through and expand that, you're left with 4xy plus the natural log of x squared plus the natural log of y is equal to 7. That 2 comes in front. So it's 4xy plus 2 natural log of x plus natural log of y is equal to 7. Okay, 4xy. We have the product rule again. It does not matter where you put the 4. You can either put the 4 with u or with v, but you need to have both of them. So if you say u is equal to 4x, the derivative of u is just 4. And v is equal to y. Well, and then the derivative of that is just dy dx. So to write that out with the product rule, you have 4 times y. Again, one of them will be this piece, and the other one will be that piece, plus 4x dy dx. Now, the next piece, remember, if I have the natural log of x and I want to take the derivative of that, the derivative of the natural log of x is just 1 over x. That's our new rule for the 5.1. So then this next piece, the 2 just comes down. So that just becomes 2 over x. Same thing with the natural log of y. The natural log of y is going to just be 1 over y. That's the derivative. But because it's implicit differentiation, but I need to have that's the derivative of y with respect to x, and the constant term is just 0. All right, let's go ahead and simplify this. Anything that is dy dx is going to leave it on the left-hand side of the equation. Anything that is not gets moved to the right. So now I'm left with 4x dy dx plus 1y dy dx is equal to negative 4y minus 2 over x. Factor out the dy dx, and I'm left with 4x plus 1 over y is equal to negative 4y minus 2 over x. Now, I'm going to have to divide both sides of those, but I don't want to deal with 2 complex fractions. So what I want to do with this is I want to go ahead and find a common denominator between these. So I'm going to multiply this times y and multiply this times x. And when I do that, it gives me 2 different fractions. Now I have dy over dx times 4xy plus 1 all over y is equal to negative 4y, let me make that xy, negative 4xy minus 2 all over x. Now when I go through and do this, instead of having dividing fractions, I'll just go ahead and multiply by the reciprocal. So I'm left with dy dx is equal to negative 4xy minus 2 over 2. Multiply times the reciprocal, which gives me this is to be y over 4xy plus 1. Oops, I'm sorry. I need a 2 here. I copied it down wrong. And then multiply all of that out. And you're left with dy over dx is equal to minus 4xy squared minus 2y all over 4x squared y plus x. So what we have to do is we have to find that. That's what setting the first derivative equal to 0 does. Then after that, then step 3 is to find out if it's a max or min. And you can do that one of 2 ways. You can either use the first derivative and look at what's going on in the intervals, or you can go ahead and use a second derivative test and see if the second derivative test is always positive or always negative. Okay. So let's start off with something nice. The first derivative of 2x, right? That we all know. That's just equal to 2. Now, inside here, remember, this is u. So what is the rule? Again, the rule for this section is if you have the derivative of the natural log of u, that's just going to be u prime over u. So u prime is just 2. So this is minus 1 over 2x times 2, or 2 minus 1 over x. So the next step in that is to set the first derivative equal to 0. So now we're in step 2. Y prime is equal to 0, so then I just have 0 is equal to 2 minus 1 over x. 1 over x is equal to 2. I just move that over. And I cross multiply and divide, and I get x is equal to 1/2. So that's my critical value. Now we have to find out if that is a relative minimum or a relative maximum. So now at this point we can go ahead and do this 2 different ways. Now, first way is to use the second derivative test. So if I go from y prime, that was 2 minus, I'm going to rewrite that as x to the negative 1. The second derivative of that, the 2 becomes 0 and goes away. So that's a negative from the outside here. Negative 1 comes down in front, which turns that into a positive, x to the negative 2, or 1 over x squared. Now, what that tells me here in the rule is whenever the second derivative of a function is always positive, which it has to be because that is an x squared term, which will always be positive, and this is a positive out front, that tells me this is a relative minimum. It is opposite of what we think, but let's go back for a second. The other way we talked about doing this is using intervals. So if I come back and I say, all right, my critical value is at 1/2, I want to do a test point over here at 1, and let's say 1/10, and then plug those in. And I can't use 0 here because 0 is not inside the domain, because if you remember, we have the natural log of 2x in part of our function, and whatever is inside of that log function, that must be strictly greater than 0. So 0 is not inside my domain, which is why I want to use 1/10. So I go ahead to find out what that slope of that tangent line is. And again, remember, that's all we're looking at, right? The slope of our tangent line, where it was equal to 0 would be here or here. So we want to find out if that's a max or min. So I go a little bit over on one side of it, and that's positive 1/10. I plug that into my first derivative. And if I do that, you're going to get 2 minus 10, which is going to give you a negative value. And that's really all you need, because we know negative, so that slope is going down. If I go through and plug that back in to the first derivative on the other side, you're going to get 2 minus 1, or 1, and that side is going to give you a positive. So that line looks like this, which is why, again, that this is a relative min.